of your midterm too, but there are some statistics we're doing, so I can't post a grade yet. I will post it probably later today, before your Wednesday's class, alongside with some survey and extra credit items on Canvas. So keep an eye on the Brewing Learn announcement for our latest information regarding your midterm 2 exam. That's the first piece of administrative announcement. Second piece of administrative announcement, I won't be here on Friday, so Professor Abby Kovner will be here to give a guest lecture for the first 30 minutes of your Friday lecture. Then Qingyang will come in and help you to do some problem solving. I will also post a recording of basically me doing my version of the same topic, so you can treat it as like an additional guest lecture provided by Professor Abby Kovner, and I'll also post my recording on YouTube. And that's the two pieces of administrative question. Any question on that? Yes?
Will her lecture also be recorded?
I'm not sure if she's going to record her lecture, but I'm definitely going to do my version of the recording. Okay, sounds good. So we're in chapter 6 right now. Basically, throughout this entire quarter, we went over from the very fundamental definition and the fundamental laws of thermodynamics. We get into the tabulated data of the thermodynamic table, and also went over how those thermodynamic tables are being measured experimentally. Now we're ready to use thermodynamics to work out something that chemists actually cares, which are like what is the equilibrium constant and how to use the equilibrium constant to solve for composition of a mixture that is at equilibrium. So for example, if you have a reaction taking place in a chamber, you want to know at equilibrium, like for example, a ammonia formation reaction, right? You have nitrogen, hydrogen, and ammonia. So at equilibrium, what is the composition of these gases in that chamber? So that's the question we're trying to answer today, is how to use the tabulated thermodynamic data along with our definition for equilibrium constant, and also what we learned about equilibrium constant to solve for the actual composition at equilibrium. And also to went over some qualitative understanding. Now at equilibrium, we're changing that equilibrium condition, right? We're raising the temperature, we're adding an inert gas, we're adding a reactant, we're adding a product. How will those effects contribute to the shift of your reaction equilibrium? So the two goals of today here. So today's lecture will more feel like a problem solving. So we'll do several problems together. It's always the structure of this course, right? We start from some abstract conceptual idea, and we have at the later end, we use those ideas to solve more practical problems. So let's get started. I think I opened the wrong note. Okay. Ideal gas equilibrium calculation. So a quick refreshment on what we learned in our last lecture. So this one is the fundamental equation we solved for in our last lecture, that delta G naught, or the standard Gibbs free energy of your reaction, equals to negative RT times the logarithm of your standard equilibrium constant. And in here, your standard equilibrium constant, K naught P, is defined to be a series of products of your partial pressure at equilibrium divided by the standard state to the power of your stoichiometric coefficient. And in here, the first part, when we're talking about the delta G of the reaction at certain temperature, that's the summation of your stoichiometric coefficient times the standard Gibbs free energy of formation at certain temperature for that species I. And these you can find from the thermodynamic table. Or you can also calculate it using G equals to H minus TS. All right. So now we have all these tools in our toolbox. How do we use it to calculate equilibrium composition for an ideal gas reactions? So here are a few steps. We'll go over those steps first, and then we'll do some example problems together. The steps are the following. So first we calculate delta G naught, or the Gibbs free energy of the reaction, at certain temperature of specific chemical species involved using our thermodynamic table. Then you use delta G naught equals to negative RT ln K naught P to solve for what your equilibrium constant is from your Gibbs free energy of the reaction. Now, if we're talking about a reaction that is not taking place at your standard temperature or room temperature, you can use the Van Hoff equation to solve for how your equilibrium constant change with respect to temperature. Next up is to express your equilibrium Moore number. So this part, let's review a little bit on what each of the terms mean, and we'll see an example together. It's actually pretty straightforward. Now, on the left-hand side, this Ni equilibrium, that's the number of Moore, or number of Moore, N Moore, of species I at equilibrium. So for every chemical species involved, you have one of these equations to represent what is the number of Moore of that species at equilibrium. On the right-hand side, you have the initial number of Moore. So this 0 here stands for initial, not for 0K. And here, on the right-hand side, you have the change, or the delta N, of that chemical species I. So this is our stoichiometric coefficient. And at the end, you have this weird term, that's your extent of reaction, or C. Now, once we know these number of moles of species at equilibrium, we know what the partial pressure of these species at equilibrium, because we're talking about ideal gases, right? Your partial pressure equals to chi times, or the Moore fraction times the total pressure. So you can express your partial pressure using the extent of reaction. And finally, you can plug that in back to our equation to solve for this extent of reaction and calculate the equilibrium composition. So let's just look at this part first. What do you mean by express equilibrium Moore numbers? And then we'll do a full example together in how to solve for equilibrium composition. So this part, again, we'll use our ammonia production example in this case. We're assuming fixed volume, and we're assuming ideal gases. So what we mean here is we have this table to solve for how much reaction has been taking place and what is your expected number of Moore of each species at equilibrium. So in this case, what do we have is your delta N of each chemical species, equals to your stoichiometric coefficient times the extent of reaction. So that means for nitrogen, let's say our stoichiometric coefficient is -1. So the delta N for nitrogen will be negative C. For hydrogen, your stoichiometric coefficient is -3. It's a reactant. It's negative number. So that's -3C. For NH2, the stoichiometric coefficient is 2. So that becomes 2C. And your final number of Moore of species at equilibrium, so N equilibrium equals to N naught plus delta N. So that becomes quite obvious, right? You just plug these two numbers together to get 1.0 minus C, 2.0 minus 3C, and 0.5 plus 2C. All right, so that's what we mean by express the number of Moore of different species in extent of reaction. Now, with that in hand, we can use this expression and our ideal gas law to get more information about the system. For example, we know that the total number of mole of all your chemical species adds up together. That equals to the summation of your Ni equilibrium, right? So that in this case, if you sum all these three numbers up, you get 3.5 minus 2C. All right, so that's your final total number of moles. With this in hand, there are lots of things you can calculate. Now we know the total number of moles, and we know that each species, what's the number of moles of each species. So obviously we can calculate for our partial pressure, that equals to our mole fraction times the total pressure. And for whatever species you're interested in, you have Ni equilibrium divided by N total equilibrium times P. Right, so for example, if we're caring for, let's say, ammonia, so this one will be the pressure, the partial pressure for ammonia at equilibrium will be the 0.5 plus 2C divided by N total, which is 3.5 minus 2C times P. All right. And at the same time, we have an expression of the instantaneous partial pressure here. So with fixed volume and also PV equals nRT, you also have the partial pressure equals to number of mole times RT over V. So there's a relation between your partial pressure and the number of mole of species. And now if we know what the equilibrium constant is by plugging numbers using the thermodynamic data, we have a way to solve for our extent of reaction and thus know how your reaction is going to proceed, or what is the final composition at equilibrium. Now, before we move on, we have one more concept we need to define, which is reaction quotient. Now, equilibrium constant is the reaction quotient at equilibrium. And in this case, or at equilibrium, your reaction quotient equals to equilibrium constant. But when we're moving outside from equilibrium, the relative value between your reaction quotient and the equilibrium constant tells you which direction the reaction is going. So for example, if we have the QP, the reaction quotient defined to be the partial pressure of NH3 with its stoichiometric number, and also like N2 and NH3 of its stoichiometric number. So when we have the QP larger than KP, what we are saying is a backward reaction. And chances are, if you have like QP smaller than KP, you have a forward reaction. We'll see more example on the reaction quotient later on. But before we do that, let's just look at an example together. So this one is what we're saying, the example, this one is the example we just said, like using the tabulated data to find out the equilibrium composition of a specific reaction. So we'll read the problem together. So suppose we have a system that initially contains 0.3 mole of N2O4 gas phase and 0.5 mole of NO2 gas phase. And the equilibrium goes like this, right? So it's a decomposition of the N2O4 into two molecules of nitrogen dioxide. And we say the equilibrium is attained at a given pressure and temperature, so 25 degrees Celsius and 2.0 atm. So find the equilibrium composition. So for example, in this question, when we say find the equilibrium composition, you can express it in the number of mole of N2O4 at equilibrium, or a number of mole of NO2 at equilibrium. Or you can express it as the mole fraction of these two species at equilibrium. And we'll see how to do it. So let's turn on the light and we'll see them. I'm gonna keep it here and we'll just do our solution on the board. You can also find that on our annotated notes. So remember, the first thing we do is use the tabulated data to find out what is the delta G of the reaction. So that's our step one. We're saying our delta G of the reaction at 298 Kelvin. That's the summation of your stoichiometric coefficient and your Gibbs free energy of formation, the standard Gibbs free energy of formation. So in this reaction, we only have two species, right? You have the product, which have a 2 in front, so 2 times that NO2 gives free energy of formation, which is, I think I got this wrong. No. So check your table and make sure I have that number correct. I think I have that typo in my annotated note. So this one is for my NO2 gas, minus 1 times your N2O4, which is 97.89. And these are in kilojoule per mole. So I think this number is wrong there. So let me just correct that. If you have a thermodynamic table with you, please help me check it and see if I get it. Okay, and we can do that calculation, and that ends up to be like 4.73 kilojoule per mole. So that's the first step, just reading the thermodynamic table. Second step is using delta G naught equals to negative RT ln K equilibrium. So in here, we have our delta G naught, which is that number here. We have our gas constant, we have our temperature. We're just solving for the equilibrium constants. So what do we have is you set up this calculation to be 4.73 kilojoule per mole equals to negative 8.314 times 10 to the negative 3 kilojoule per mole per Kelvin times 298 Kelvin times ln K naught. Just plug in numbers, but make sure you're using the correct gas constant. We can solve for our K naught equals to 0.148. Am I writing too small, or you can see it from the back? Do you okay?
Way too small.
Okay, I'll write bigger. Okay, so from number one, I'll just erase these calculations and keep a number here. So from number one, what we have is delta G of the reaction equals to 4.73 kilojoule per mole. And the equation we're using is just sum them up. For step number two, we're using delta G equals to negative RT ln Kp, and our result is Kp equals to 0.148. And the next step is using our initial situation, initial condition, and also our extent of reaction C to express the number of mole of these species in equilibrium. So what that means is when you have something like, we have like N2O4, and you have your NO2 as a product. When you put that here, so number of moles, your initial number of moles is given in the question. So your initial number of mole of N2O4, that's 0.300. Initial number of mole of NO2 is 0.500. And our delta N, or how much that number of mole is going to change from the initial state to the equilibrium state, is given by the extent of reaction C. So for every molecule of N2O4 decomposed, we have negative C, and for every molecule of N2O4 decomposed, we're generating 2 molecules of NO2. So that's +2 extent of reaction. And taking that together, we have N equilibrium, which equals to N naught plus delta N. And here the delta N equals to stoichiometric number times C. So here, adding it together, we have 0.3 minus C and 0.5 plus 2C at equilibrium. And your N total at equilibrium equals to this number plus this number. That gives you 0.8 plus extent of reaction. All right. So with that in hand, we can calculate the partial pressure of each of the chemical species at equilibrium. So the partial pressure of NO2 equals to the mole fraction of NO2 times pressure, and that equals to the NO2 that's here, 0.5 plus 2C divided by the total, so 0.8 plus C times the pressure. Likewise, for N2O4, we're talking about the equilibrium of N2O4 times pressure, the mole fraction of N2O4 at equilibrium times pressure, and that equals to 0.3 minus C over 0.8 plus C times pressure. All right, so nothing fancy, just write out the expression of your partial pressure using the mole fraction. Then what we have, now we know that your Kp equals to the product of your partial pressure over the standard pressure to the power of stoichiometric coefficient. What we're doing next is to use this equation to solve for our stoichiometric coefficient. So what do we have? We have Kp equals to the product of P NO2 equilibrium over P naught to its stoichiometric coefficient times P N2O4 equilibrium over P naught to its stoichiometric coefficient. So we can plug in some of our numbers here. Yes?
The P for the partial pressure, is that the 2 ATM?
Yes, that's a 2 ATM.
And then the standard one, is that
1 bar.
1 bar? Okay.
And we will take consideration of that when we plug in the data. So, while we're plugging the number here, can I erase that part? Okay. So when we plug in the number, we have the Kp naught equals to 0.5 plus, am I doing too small here? So, okay, nevertheless. So this one, the partial pressure here is this number. So that's in here. And this is the partial pressure we're plugging here. So in case it is too small, you know what I mean. So when we plug that in, we have Kp naught equals to 0.5 plus 2C over 0.8 plus C, and P over P naught to to the power of 2, because your NO2 is in the product, your stoichiometric number is 2, times 0.3 minus C over 0.8 plus C times P over P naught to minus 1. So in here, because we're talking about your equilibrium constant shouldn't have any unit. So here is when our unit all cancel out. So inside here, when you do P over P naught, so these unit all cancel out. And in here, you both have number of more on top and below, so they also cancel out. So your equilibrium constant doesn't have any units. Now in here, we have our P over P naught equals to 2 ATM divided by 1 bar, and that gives you about 2.027. And we know this Kp naught equals to 0.148. We just solved it here. So this effectively becomes a quadratic equation. You can plug in your calculator to solve for it. If you don't have a calculator, I highly recommend you get a scientific calculator ready for your exam and homework. Now solving that quadratic equation, so this thing equals to here. We have the extent of reaction equals to negative 0.324 more. Or you have two different answers for that quadratic equation. You have that to be 0.176 more. So there is a problem here. When you have two solutions of your quadratic equation, only one of them is possible. So if you remember in our initial condition, we only have 3 more of your N2O4 available as a reactant. So we have to cross this out because we don't have enough starting material in there. So you have to use a little bit of common sense at the end after solving the quadratic equation to say which one of these solutions is the correct one to use. Now with the extent of reaction, then it should be very straightforward to calculate the number of more of each species present at equilibrium. Okay, any question before we move on? Except that I'm writing too small. Didn't get? All right. So next up is also an example problem. So this one is not as quantitative or like algorithmic comparing to that example. This one is more like a derivation problem. So the take-home message here is we don't express our answer in numbers, but we develop the intrinsic connection between these properties. The question reads, suppose a gas phase isomerization, you have A, B isomerized, A and C isomerized, and B and C are also isomerizing. So you can imagine you have one compound that can undergo, that isomerize with 2 other compounds in a triangle. And it reach equilibrium at a fixed temperature. Express the equilibrium mole fraction of A, B, and C in terms of equilibrium constant. So what does this mean? So this means your equilibrium mole fraction is related. You can express your equilibrium mole fraction using equilibrium constant alone for all 3 of them without plugging number. So how do we do that? Let's consider our first reaction, which is between A and B. So I express our equilibrium constant as K BA. So that just means BA equilibrium constant. Now, by definition, that equals to your PB, your partial pressure of B over P naught divided by PA over P naught. Now, PA is on the bottom because PA is your reactant, has a negative in its stoichiometric coefficient. And for ideal gases, we can express them to be your mole fraction chi B times P over P naught divided by chi A times P over P naught. Or since the pressure is the same, we can cancel out these terms, and our equilibrium constant between A and B effectively becomes chi B over chi A. Or the other way to put it is your equilibrium constant KBA is a key to connect your mole fraction of A and mole fraction of B. So what do we have here? Is your chi B equals to chi A times K BA. So the first one is checked. We are expressing your mole fraction of B using mole fraction of A and equilibrium constant. Next up, what about A and C? So your K, Ca, using the same derivation, you can write that out as chi C over chi A. And also for your B and C equilibrium, you can write the expression as like KCB equals to chi C over chi B. It's the same kind of derivation. But we know something more about these with these mole fractions. Or the other way to put it is your mole fraction is inherently connected. So what that means is your total mole fraction must add up to be 1. So chi A plus chi B plus chi C will add up to have to be 1. Or the other way to put it, because right now in our expression, we have both a mole fraction and the equilibrium constant. What we want is using only the equilibrium constant to express what the mole fractions are. So for that, we have to use this relationship here, that your mole fraction adds up to be 1. So with that in hand, what we have, now your chi A here then becomes, or this expression, that if we keep the chi A here, we have chi A plus your chi B equals to chi A times K B over A plus here your chi C equals to your chi A times K C over A. And this adds up to be 1. Or if you take that mole fraction out, the expression we end up having is chi A equals to 1 over 1 plus K BA plus K CA. Didn't get? So effectively, what this part is demonstrating is, again, why do we care about thermodynamics? It's by knowing the rules of thermodynamics, you don't necessarily need to know what each species are at equilibrium. You can derive it using only the thermodynamic equilibrium constant. And try that for your species B and C and compare your answer with our annotated note. Okay, any questions before we move on? Nope? Okay. The next question, we're moving on to our chapter 6.6, where we're looking at shifts in equilibrium gas reaction equilibria. Shifts in ideal gas reaction equilibria. So in this case, we're coming back to our reaction quotient. Remember, our reaction quotient is defined when you have for a reaction, for any reaction that has stoichiometric coefficient mu I times the chemical potential. Well, not chemical potential, I should say this one is a species for a random reaction. And the reaction quotient is defined as your product of your partial pressure with the stoichiometric coefficient on the power. And in this case, we are comparing it with our equilibrium constant, Kp. Of your partial pressure at equilibrium divided by standard pressure with a power of stoichiometric coefficient. And the sum of the take-home message is when your reaction quotient equals to your equilibrium constant, that's at equilibrium. When your reaction quotient is smaller than your equilibrium constant, that is a forward reaction. And when your equilibrium quotient is larger than your equilibrium constant, that's a backward reaction. Okay? And this part I have to double check. In your textbook, it gives you this expression, but I'm pretty sure you have to divide that by your standard pressure as well to cancel out the unit. This one I have to double check and make sure I have it correct, but that's the expression your textbook gives. Okay. With that in hand, we will first go over some of the general situation in like, what are the things you should predict at a fast rate? So as you see in our midterm 2, sometimes when you have like multiple choice equation kind of problems, you do not want to necessarily do a long derivation or a calculation to get to the answer. So this part is trying to give you some qualitative understanding in how change of different factors or change of different properties will affect your equilibrium position. So the first example we're looking at here is called isobaric temperature change. So isobaric temperature change means we're holding the pressure constant while changing the temperature. So because we're holding the pressure constant, now that means your reaction quotient or your partial pressure is not changing. For the same reaction, your stoichiometric coefficient is not changing. Your partial pressure is not changing if the pressure is held constant. So your Q remains the same. Now, in order to predict how equilibrium moves when you have the isobaric temperature change, what effectively we're asking is how does my equilibrium constant change? Right, so before at an initial temperature where your reaction quotient equals to equilibrium constant, that's at equilibrium. Now say we're rising the temperature or we're decreasing the temperature, how does the equilibrium respond to that temperature change? So we're using our Van 't Hoff equation. So remember, that's how we derive the dependence of your equilibrium constant on temperature. So in this case, on the left-hand side, we have the ln of Kp over T. So let's just think about how does your Kp change over T, because that's what we care about, right? So in the Van 't Hoff equation, we have to do some calculus. So for example, the ln Kp over dKp or dk naught. So this just gives you Kp naught 1 over Kp naught. Or the other way to put it is your d ln Kp naught equals to 1 over Kp naught times d Kp naught. So that gives us, so plug this back to here. It gives us the expression of d Kp naught over dt equals to, let's see, ln Kp equals to right, that's true. So on it should on the right-hand side, that's the Kp naught times a delta H naught over RT squared. All right. So one of the questions here is when to use calculus. Again, we use calculus trying to solve a chemical problem or a physical chemical problem. So in this case, what we care about is how is your equilibrium constant change with respect to time. So we know we want to find something like dKp naught over dt and everything else on the right-hand side. So that is why we went back and do our calculus to find out what is the expression of dKp over dt. And from here, there are several pieces of information we know. So for example, our equilibrium constant, it comes from a logarithm function. It's always going to be positive. Your r and t squared will always be positive. So these are all positive. So that tells us how my equilibrium constant change with respect to temperature is dependent only on the thermodynamic nature of that reaction of interest. Or the left-hand side is only related to how your delta H change, if we're talking about the sign. The magnitude might be different, but if we're only talking about what is the sign or which direction your equilibrium is going to go, only knowing the nature of the reaction is good enough. What does that mean? So let's assume we have a positive delta H. So a positive delta H means your reaction is endothermic between your reaction and product. So that tells us our dKp naught over dt is positive. So when this differential is positive, what we're looking at is when temperature increase, your equilibrium constant will also increase because the differential is positive number. All right. The same applies to reactions that are exothermic. So we have negative delta H naught. So your reactant is higher in energy comparing to your product. So your reaction releases heat to form a more stable product, and that's an exothermic reaction. And this differential of your Kp over dt is negative. So that means when your temperature increase, your Kp naught will decrease. All right. And that leads to a general conclusion. Now, we did all our derivation here using ideal gases, but this conclusion is generally true not only for ideal gas reactions, it's basically for any chemical reactions. An increase in temperature at constant P in a closed system. So we care about constant P because, well, at normal condition with the atmosphere in play, we are talking about constant pressure. Now, an increase in temperature at constant pressure in that closed system will shift the equilibrium in the direction in which the system absorbs heat from the surrounding. So, depends on how you want to remember it. If you want to remember it as a word, that's possible, or just remember it using the Van 't Hoff equation and derive it whenever you need. Yes.
Is this only true for small temperature changes, or?
In general, I think it's okay. So, don't take it as like 100% true. I have to double check on that. But I believe it's generally true, not only for small temperature changes. I have to double check on that question. So send me an email and I'll check it for you.
I think I'm just confused with like enthalpy change is still temperature dependent, like for a reaction.
Right. So in this case, the question becomes like whether we can still use that delta H naught for the standard state, or will that delta H naught change if my delta T is too big? So that means like, if we're talking about like chemistry reactions on planet Earth, not like thousands of degrees of temperature change, it's probably true. But if we're talking about like an explosion where you have like 5,000 K temperature change, then things will become a little bit more complicated. Okay? All right. The next topic here is the isothermal pressure change. So this one is more related to the number of gas molecules involved, because we're talking about pressure change. If you have like liquid or solid involved, typically their volume change is very small and they do not contribute to your overall pressure change. So in this case, we're focusing on gas-phase reactions or the number of gas molecules in your reactant and product. So from the very beginning, if you think about the isothermal pressure change, what do we have? It's at the initial state or equilibrium state. You have your PA, or the partial pressure of your species A, equals to chi A times P, and your partial pressure of B equals to the mole fraction of B times P. Or the other way to put it is we have our reaction quotient. So QP at our initial state or at equilibrium, that equals to your KP. And you can express that as the product of your chi A times P negative A and chi B times P to the coefficient B. That's the initial state. Your reaction quotient equals to equilibrium constant. Now assume we have an instant change of state. Now your second state, your pressure equals to 3P. So we're having the P2 now changed to like 3 times. We triple the pressure at a new state. The question becomes, how do we predict the direction of your equilibrium to shift? So in this case, we're dealing with gas-phase reactions. And for ideal gases, if you increase the pressure to 3 times, you'll basically decrease the volume to 1/3. So this part is for gas phase. And how do we predict the direction of the equilibrium shift? So again, recall our Van 't Hoff equation. We're not use it. We're just saying your Kp naught is constant at constant T. So we're talking about an isothermal pressure change. So the temperature is not changing. Your equilibrium constant is not changing. But your reaction quotient might. So in this case, your Kp is not changing, but your reaction quotient equals to, again, chi A times 3P negative A, chi B times 3P at B. Now, in this case, the change inside the bracket is the same for your reactant and product. So when we compare how your reaction quotient is going to change, that depends on how your stoichiometric coefficient compare to each other. So the take-home message here is if your stoichiometric coefficient A in the reactant is smaller than that of the product, we have backward reaction. We're synthesizing more gas molecule and we're having the reaction going backwards. And vice versa, if A is larger than B, your QP is smaller than KP, we're predicting a forward reaction. So we end up having the general rule again. So an increase of pressure at constant temperature in a closed system will shift our equilibrium in the direction in which the system volume decreases. Okay. All right, I think that's all the time I have today. In our next lecture, we'll go over a few more situations. For example, the isochoric addition of inert gas and also adding your reactant or product and see how do they affect your equilibrium position. And also do an example problem together. Okay, I will see you on Wednesday. I'll post your